So I'm interested in the state diagram and state table when we get to it. Then we'll deal with the flip-flops after that. We didn't discuss them. But just to show you what that is. Let's say you're designing a soda machine or a candy machine, candy bar. It's going to sell Kit Kat candy. One candy, that's it. I like Kit Kat. Nothing else. Kit Kat. Is it Kit Kat? Yep. Now, how much the Kit Kat's going to cost? What do you want? $1. Oh, that's too much money. Let's say 20 cents.
We'll just see what they do with the vending machines.
You'll see why I decided not to do $1. And your machine is going to take nickels, dimes, and quarters, and that's it. Input or inputs, 5 cents, 10 cents, 25 cents. You have to look at, like, visualize how that machine, because I could walk to the machine and use only nickels for that machine. So I could have a zero state, zero money. When you walk into the machine, nobody put any money. It's waiting for us to put money in it. It says zero money in it right now, that state. And what will happen if you put 5 cents in it? You're not going to get anything, right? But the machine should move to a stage called 5 cent state. And if you're at the 5 cent state and you put another 5 cents, you're going to be where? At 10 cents. You're not getting any candy yet. If you're at the 10 cent state, you put 5 more cents, where do you go? 15 cent. And if you're at the 15 and you put 5 cents, what will happen? Nope, it should go back to the beginning.
Oh, the 20, yeah, it's 20, I thought it was 25.
It's going to give you what now? One candy, right? You get a candy. Should spit a candy out. But what happens if I come into the machine, I put 5 cents, then I put 10 cents after the 5 cents. You go right there. No candy. Or maybe when you started the machine, first thing you did, you put what? 10 cents. You go right here. No candy. If you're the 10 cent state and you put 10 cents, what do? You go back there.
You get candy.
You get a candy, yep. What about if you were at the 15 cent state and now you put 10 cents or 5 cents? We did the 5 cents. If you put 10 cents, you go right there. You get what? Candy and what else? You have to get 5 cents back because you're 25 cents. If you walk into the machine the first time and you put no money, what happens? You stay there. So while you're thumbing through your pocket, the machine is waiting for you. The clock is moving faster than you are. So it's checking, 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 checking. You're not putting any money. If I put 0 cents, I'm staying here. I'm not going anywhere. I get the 10 cents, and now I'm looking for that. I know I had 2 dimes. I put it 5 cents or 10 cents, and I'm looking, where's my other dime? And I'm looking. The clock is checking. I'm not going anywhere. The machine should stay right there. But now what happens if I'm here, I put a quarter immediately? You put 25 cents, you'll get what? candy, and what? And 5 cents back. What about you put 5 cents first, then you realize the only thing you have left in your pocket is a quarter. So you're going to go back there now. If you put 25 cents, you get what? Candy, and what else? 10 cents. Start to get ugly. That's why I said $1. If I put $1, I'm in trouble there. If you're the 10-cent states and you put 25 cents, you get a candy back. What else? 15 cents. And if you're the 15, you put a quarter back. You get a candy. And how much back are you going to get back? 20 cents? No, it's just simple design. Look how ugly it looks like. So when we talk about these state diagrams, you say, what are you getting these states from? So we'll label these states. Since I only have 4 states, I might call this state state 0, 0. I make a code for it. If I see 0, 0, that means that state no money. If I see 0, 1, that's state 5 cents. If I see 1, 0, that's a state 10 cents. If I see 15, that's a state what? 1, 1, 20, 15 cents. Now, if I made the candy actually 25 cents, right? Then I will need one more here. Guess what will happen now if I did one more? I'll have 1, 2, 3, 4, 5 states. 2 inputs will not do it. I will need 3 inputs. So it'll be like 0, 0, 0 to get this, 0, 0, 1 to get this, 0, 1, 0 to get this, 0, 1, 1 to get that, 1, 0, 0 will be the 20 cents, 1, 0, 0. So what are you going to do with 1, 0, 1, 1, 1, 0, and 1, 1, 1? You have 3 unused states now. You, the designer, you will have to decide what do you want to do with them. Now you might say, you know what, I'm going to keep the money. You can. You design the machine. Or, I'm going to give them a candy bar and give them 10 cents back. Again, you're the designer. Why 10 cents? Because you like dimes. I don't know. But usually you want to look at it in terms like, it's not going to happen that often, and I don't want somebody to break my machine. Some people, if they're hungry, they get really angry, and they start kicking the machine and shaking the machine. Is it really worth losing that machine over 10 cents or 20 cents? Give them the candy bar, give them 20 cents, they can have it. They didn't put more than 20 cents in it because the machine has only a quarter. You can give them 25 cents if you want. But if you give them 20 cents in a candy bar, I'm sure they're not complaining. If they walk to the machine to get a candy bar and they put 25 cents or 10 cents and the machine found itself somewhere there, a state I'm not using, suddenly a candy bar drops and some money, they're not going to be angry. They're not going to shake the machine. So that becomes, okay, might be a better choice to do that. So you could end up with don't care situation or not use situation. You can say, I'm going to use them, don't care. I don't care what the machine does. It's not my machine. I'm selling that machine. Let them break it. They'll buy more from us. You could do that. But if a lot of machines start to break down, nobody's buying the stuff from you. And I said, I'm not buying this machine. It only lasted 6 months, then it died. You know? So today we're going to, well now at least we're going to be looking at state diagram. Now some people, the way they draw these, they put the slash here or the slash under where you get them back. So I'll introduce you to some of these topics. So there's a picture here, and we'll see if we can go from this to the state table. I'll make it less complicated than this. This is too much right now. But I want you to see where they're coming from. Here we have actually these states. We have state A. And if you're a state, there's your output. You get nothing if you're a state A. See that at the bottom? That's your output. That's how they decide to do it in this, just in this example. So this is state B. Your output is 0 again. If you're state C, you also get no output. Could be candy, but no money back here. And state D, you get 1 for an output. So you have 4 states. If your input is 0, you stay right there. If your input is 1, you go right here. If you are state B, and if you put a 0, you go right there. If you put a 1, you go to this one. If you put a 0, you go right here. If you put a 1, you go right there. If I put a 1, I stay here. If I put a 0, and I have no idea what that table represents, but this is the picture I got. Can I go from this state diagram to the state table? Let's look at my state table. So this is the current state. This is my next state right after it. And I forgot to put the input. This is my input. I'll put it here. And this is my output. I have 4 states, and each one has 2 options, so it should be 8 altogether. 1, 2, 3, 4, 5, 6, 7, 8. Let's begin with state A. Twice. If my input is 0, this is state A. When you're state A, what's your output always? 0. But if I'm at state A and I put a 0, what will happen? If my input is 0, where do you go? You stay where you are, and your output is 0. But if I'm at this state and I put a 1, see that? You put a 1, where do you go? State B, and what's your output in state B when you get to it?
0.
0. That's called a state table. If you are a state B, we're going to look at both cases. If you put a 0, go back to A, and up and A, and what are you getting? Nothing. If you put a 1, where do you go? State C, right? And what's your output? 0. Let's look at state C. If you put a 0 in it, what happens? You go back to A and you get nothing. But if you put a 1, you go where? D. Do you have an output now?
Yes.
1. Yes, 1. And if I'm a state D, if I'm a D and I put a 0, what happens?
A.
You go to A and there's no output. And if I put a 1, what happens?
B.
And you end up with 1. So notice my output, where I'm going in my output depends where I am, the current state where I am at, and if my input is 0 or 1.
Do you always expect the outputs to match the variable, not the variable, but the 2 to the n?
Well, here notice you have how many states? You have 4 states. So if I was to assign them like digits, I will have to use 2 variables. So this was state A might be called the state 0, 0. You know? State B will be known as 0, 1. State C will be known as 1, 0. So in my mind, in my programming, if I see 1, 0, that means C. State D will be 1, 1. Because you're not going to use A, B, C, D. That's just for us to understand that. So I will be using these as to tell me where I am. If I see 1, 1, that means D. If I see 1, 0, that means state C. If I see 0, 1, that's B. If I see 0, 0, that's A. Again, I have 4 states. That's why I use 2 digits here. If I have 5 states, I got to use at least 3. And there'll be some unused. So this is going from a state diagram to a state table. Let's try another one. Here's my state diagram. State A, state B, and state C. If I'm at A and I put a 0, I stay there, end up with a 0 for an output. Notice my output now is slash, different than the other notation. If I put a 1, I go to this one. If I'm at B and I put a 0, I get a 0. If I put a 1, I go right there. If I'm at state C and I put a 1, if I put a 0, so here I only have 3 states.
So is that input and output?
That's the input, and that's your output. So the way it's defined, yep, input slash output. That's how it is, John. Yep. So I have the current state, my input. So this will be current state. This will be the input. This is the next state where I'm going to go. And this is my output. So current state, input, next state, output. And I only have actually 3 states here. 1, 2, 3, 4, 5, 6. I don't need 7 and 8 because I'm not using them, but I want to highlight them a little bit there. So if I'm at state A, and if my input is 0, where do you go? A, and what's your output? 0. Output. If you're state A, you put a 1, where do you go? B, and what's your output? 0. If you are state B, you put a 0, you go to A, your output is 0. If you put a 1, you go to C, and your output is 0. And if you're state C now and you put a 0, that's right there, you go back to A and your output is what? 0. But if you're C and you put a 1, you go where? Back to C and your output is 1. I left these 2 there intentionally, 2 more states. Again, since you have 3 states, you will need 2 digits for that. So I might call state A is 0, 0, B is 0, 1, and C is what? 1, 0. So what do you do with 1, 1? So we have here unused states. And again, you're the designer, you got to decide, if I see 1, 1 in my input here for the current state, what do you want the machine to do? Do you want the machine to reset itself and go back to this one, start from the beginning? Depends. What are we designing there? There's no way for us to know when the machine's going to get to that state. So you can't say, well, it got to it after C. There's no way of saying that or knowing that. It could happen from the beginning. Boom, it goes to this one. And you can't leave it blank because you got to tell the machine what to do when you hit that state. So a lot of people say self-reset, meaning what? If A is the beginning, go back to state A. Start from the beginning. Go ahead, shake the machine. I don't care.
How does it get there though?
Could be any reason. Could be a short circuit. Some crazy thing that happened, low power, high power, spike. Suddenly, boom, you find yourself there. You know? So if that happens, it's not going to happen that often. Maybe the life of the machine, maybe once or twice. But if that happens, you want to have a safety, a backup plan. What do? It's not going to happen every single day, once a week or a month. Maybe it will never happen. But I want to make sure if it does happen, I don't want the machine stuck there, now nobody can use it. Just like you're doing something on the computer, freezes. Why does it freeze? Something went wrong there. What was it? I don't know. Just machine found itself somewhere it can't get out of it. What's our solution? Unplug it, and plug the power back in, hopefully it resets itself. We can do the same thing. We can say, it finds itself somewhere there, I don't care what you do, I'm going to go walk into the cord, unplug it from the wall, plug it back in. But whoever put money in that machine now is not happy because they lost that money. The machine took it. On campus here, you can go to account, and they'll give you a piece of paper. It says, oh, I put 50 cents in the machine. They'll give you that 50 cents if you don't get your soda. You fill a form, you give it to the vendor machine when they come here, and they give them the money. Because they don't want people shaking the machine. So we need some devices that will say, okay, my output is not going to depend just on the input alone. Where I'm going to go next, it depends on two things. What is my input and where I am. And these are the flip-flops we have on the market. We have different flip-flops on the market, and we have them in the lab. We'll be playing with them. So let's look at some of the flip-flops. Flip-flops, FF. And there's different type of flip-flops. We have D flip-flops, we have JK flip-flops, we have SR flip-flops, we have SR, JK, D flip-flops. I'm just thinking what I have in the lab there. T flip-flop, toggles, I have that too. We have different flip-flops. Some are clock, some are without a clock. So let me look at the first one, D flip-flop, data flip-flop. D flip-flop, data. The way that flip-flop works, has only one input and two output. All the flip-flops actually have two outputs. One is the output, the other one is the complement of it. So this one looks something like this. I don't need to be that big. It has, some has a clock, some doesn't. I don't care about the clock for now. Maybe I'll mention the clock just briefly. And I have two outputs. We'll call them Q. And the other one output is the complement of that. So this is Q, and this is Q naught. So when this one is 1, this is 0. When this is 0, this is 1. Now, I want you to pay attention to the clock. if you see the clock here, looks like this. That means this works on the rising edge as the clock goes from 0 to 1. So when the clock goes from 0 to 1, the output here will depend on whatever D is. On the other hand, I'll make the other one in red color. If the clock looks like this, with the bubble in it, you're not going to have both, one or the other. But if it looks like this, a little bubble on it, that means this is going to work on what? It's called the falling edge as the clock goes from 1 to 0. This on the rising, this is on the falling. As the clock goes from 0 to 1, the value of Q will depend on D. If it's this one, the clock, as it goes from 1 to 0, that's when we look at it.
When you say clock, is it like an actual timer?
Yep, there's a clock, just like your computer has a clock in it. It makes all these square waves, you know. Now the ones in the lab wouldn't have a clock on them. So guess what the clock is? You. Go on. With the switch. Every time you flicker, that's the clock. You know.
So is it actually timed or is it just specific?
No, there's no timer like the ones we have. These actually, when you design a computer, you want everything to be synchronized.
Yeah.
You don't want this to be flickering when I'm waiting for something and this just doing its own. You want everything to happen at the same time. That's why we have a clock inside them. So when the clock goes to 1, this one will check to see what this and feed the result.
So it's not really based on time then, in terms of...
Well, the clock will be like 10 nanoseconds every pulse.
Oh, okay.
So you have a square wave that comes in inside your computer. There's a square, like if your machine has 2.9 megahertz, what does that mean, the clock? 2.9 million pulses every second. So on the rising edge of that, if it's this, we'll look to see what's happening. If it's that one, on the falling edge.
Okay. So you just change the output based on the clock, or based on the input?
We'll paste on D.
Yeah.
Yep, and where the clock is. Yep, I'll give you an example.
Okay.
So the way D works actually, the way versus Q, it's called D flip-flop, which is data. That means your output really follows data. So when D is 0, regardless what the previous stage is, doesn't matter. Your Q will be 0. That's the way this flip-flop works. When D is 1, your output is 1. That's where the name data flip-flop came from. So let me draw a picture for you let me do a timing diagram. Where's my graph paper here? Let me see. Not here. I was hoping I have that one here, but it's not. I'll use this one. So let's see how it works. Let's take a D flip-flop, and I'll make it work on the falling edge. Like I'll make the clock like this. So here's my D flip-flop. Quickly. So there's my D flip-flop. Here's my clock. I'm going to make the clock. See the bubble here? That means on the falling edge. So as the clock goes from high to low, that's when we pay attention to it. So it has two outputs, that's Q and Q naught. So let's make a clock here. This is the part I don't want to draw. You know what? I better count. It makes my life easy. 1, 2, 3, 4. One, two, three, four. 1, 2, 3, 4. Okay, here's my clock. Has zeros, ones. Can you see it? That's the part I don't have to draw. I made copies of this, but I don't know where I put them. Can you see the clock now? That's your clock. Let me put values for Q. Now I'll make something up. Q has a value of 0 for a while. Then notice how far I extended it. Then it goes to 1. That's Q. And stays 1 maybe to here. Then it goes back to 0. Then stays 0 till somewhere here. Then it goes back to 1 again after that. That's what Q is. Well, actually, that's D. D. Not Q. That's the input. Let's look at Q. So let's see what Q will look like. Now, most of these have a reset button. Now, almost all of them have a reset and set button. What does that mean? You can either start from 0, or that's a reset, or make it 1, which is set to 1. So it's really up to you where you start from. Yep. So there's a button on two inputs there. If you attach a VCC to reset, it makes it start from 0. If you attach it to set, it makes it start from 1. So here, it's really up to you what you want to start at, 0 or 1, based if you hit the reset or set. So I'm just going to go like this. You decide where you want to start from. It's not important here. So you can start from 0, you can start from 1. If you hit set, it will start from 1. If you hit reset, it will start from 0. But there's the part. Notice this one works on the falling edge of the clock. Nothing happens till we hit this time. See this time here? That's the falling edge. The way this clock works looks at the falling edge. We don't care what happened to the data. So notice this Q is supposed to follow D. If you look at the truth table for it, when D is 0, what do you get? 0. When D is 1, what do you get? 1. Well, D is 0 here. Then it goes to 1. You think this is going to go to 1. It doesn't happen there. Why? Because this one only looks at it when the clock goes from high to low. Only looks at it right here. So this will stay whatever it was till we hit this time. Then what do we see here? D is 1, so we'll go to 1. So if you make that Doesn't matter where you start from, because it depends. You can set your machine to 0 or 1. So here, this stays the way it was before. Meaning what? If you had it as 0 initially, it will stay as 0. If you had it at 1, it will stay at 1. Now the clock goes from 1 to 0. What does the machine sees? A 1. Stays 1. And it will stay all the way to the next block, till the clock goes down again. Even after your data went back to 0, we don't see it. We don't care. You only look at it when the clock goes from 1 to 0. Notice what happens now. The clock goes 1 to 0. What is D equal to?
0.
So this one goes to 0. And it will stay 0 till the next clock comes in. Even when D is 1, I'm still getting a 0 here. Nope, it just only looks at when the clock goes to 0. I mean 1 to 0. Now here we go. The clock goes 1 to 0. What do we notice? D is what? 1.
I thought that was 0 still.
Nope, that's a 1 here. And that will stay 1. Now these might have a delay on them since you brought that, John, so it doesn't happen that quickly. It will stay. So it might take a few seconds for it to go there. But when the clock goes from 1 to 0, that's when I pay attention. I don't care when this one goes back to 0 or 1. So my output is always in sync with the clock. It doesn't just change when it feels like it. If I don't have a clock here, then Q will look exactly just like D if I don't have the clock. So when this one went to 1, this jumped, where this one stayed whatever it was till that time. When this one dropped to 0, this one did not drop to 0. It says, no, till the clock comes in. This one went back to 1 here. This one goes, nope, I'm not following you till I see the clock.
Could that make a huge difference?
Oh, yeah. You want everything to be synchronized, because what happens, you're in the middle of your cycle, little lightning hits here, little spike. Doesn't affect that.
Oh, yeah.
Because this does not see it till this one. Let's say we have a little spike here. Hopefully it didn't kill anything. If I didn't have the clock there, this will see that. That's what your output will look like. This doesn't see it till the clock goes down. Oh, I see a 1 here. That's not a problem. So that this one works on the falling edge because I have the little circle. If I don't have the bubble there, I'll be looking where? At the rising edge, right there, to see what's happening. Not at the falling edge, the rising edge.
So what is the point of that? What is it? What does it actually use it for?
What?
The flip-flop. Like, what would you use this for? Just to.
Remember, I'm looking for something that depends on the current state and the input. So this one, actually, the D flip-flop, it really looks at the data. But you're going to see other ones, they depend on also the current state. So if you want something that will depend on where you are plus your input, you can't just use a plain gate or PLA or PAL. You have to use flip-flops. They take into consideration your current state. So let me try another flip-flop. And notice, as I said, the flip-flop might have a preset, like this one showing you there's a preset on this one. And there's a clear on this one, on this flip-flop. So can you see it on the screen? When you hit the clear, it says about over. When you make clear equal to 0, where is it clear equal to 0? Right there. So what happens? First, you need the clear equal to 0, and you set the preset to 1. Well, preset to 1, this is not working. You can't have preset and clear both on at the same time. Preset means set it to 1. So when you make this one 0 and this one 1, this is on, that's off. Preset is equal to 0 and this one 1, that means the preset. You make in the next state equals to 1 automatically. It doesn't matter what D is. When you make this one 1, this is off. When you make this one 0, you're clearing that, you make your output 0. Regardless, what was D? To make them both low, that's impossible. Can't be, not allowed. You can't tell them, make it 0, make it 1 at the same time. Make up your mind. If you make them 1 and 1, now these guys are not a factor. Once you put 1 and 1 on them, they no longer affect what Q is. The only thing that affects Q is D. When D is 0, I get a 0. When D is 1, I get a 1. Well, this has only one input flip-flop. Some of them have 2 inputs. Let's look at an SR flip-flop. So that was the D flip-flop. So what's the SR flip-flop looks like? And why is it called SR? So the D flip-flop is called data flip-flop because it follows your data. So what's the SR flip-flop? The name SR came from set, reset. From the name set. The word set there. When you say set, that means the flip-flop is going to go to a value of what? 1. When you go reset the flip-flop, reset, that's a value of what? 0. So you have 2 inputs for this flip-flop. And again, you have a clock, and it could be on the rising or falling edge. So this flip-flop has 2 inputs. It has 2 outputs. All flip-flops have 2 outputs. It has a clock here. We didn't show you what the inside of the flip-flop looks like. We can actually figure what that is in a minute. Now I'll show you how we use them. So let's list them. So this is S, this is R, this is Q, the current state, and this is the next state. What will happen? The way the SR flip-flop works, when these guys S and R are 0, I'll make another one under it, and Q next. When S and R are both 0s, the next state will be the same as the previous state. That's how they work. This flip-flop works. Which means what? If this is really 0, if you have 0, 0 and Q was 0, what's the next state going to be? 0. When this is 0, 0, but that's a 1, the next state will be what? 1. If you have 0, 1, that's a reset. The next state will have to be always what? 0. So 0, 1, and if this is 0, stays the same. 0, 1, this is 1, it's going to go to 0. When it's 1, 0, that's a 1. 1, 0, 0, that'll go to 1. 1, 0, 1 stays 1. And what about 1 and 1, if you do 1 and 1 for them? This is not allowed. Somebody's happy. This is not allowed. You can't put set and reset at the same time. not allowed. That's how that flip-flop works. So if you're curious about what does the inside looks like, really, I know what Q next is. I can do a Kmap for that and simplify it, right? So if you do a Kmap for that, did we do it horizontally for 3 variable? I think we did it like this, right? I didn't do them vertically. If you want to know what is the inside of that flip-flop might look like, the circuit itself there, we can simplify and see what do we have. I have 3 inputs, S, R, and Q. Zero, 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 1, 1, 1, 1, 0. Let's look right here. I want 0, 1, 0, 0, 1, 1. And these not allowed, so I'll go, I don't care. If you want to make my life easy. So what does Q will have to look like? The expression for it? I can group these 4 together. And that will be what? Looks like S, right? I'm using S here. And I can take this with this, and that will look what?
R, Q.
S Q bar plus.
This will be R
Q.
bar Q. And I can do the same for the other one, for the NOT. The NOT is opposite to this. When do you want it to be 0? Well, if you group the zeros here, you can take these 4 together, right? So what are you going to have?
R plus.
I should say P, that's the previous, this is the next, right? I should label as next state, previous state. So if I group these guys, will be what? Yep, R bar. And if I take these 2 here, oh, what do we have? S is 0, that's good. And this is what? Q previous. S plus. So this is R bar S plus R bar SQ if you want to. So you can see what the inside. Oh, that's Q, not R here. That's Q, not complement. I'm doing the complement. You can see the next state depends on the previous state. Just like the next one depends on the previous, on R bar, on S. So it depends on the whatever you have for inputs here, plus what the current state is. That will determine where you're going to go next. Again, that's an SR flip-flop. Well, that not allowed bothered a lot of people. And so we can't have this one. So somebody came up with a flip-flop called JK flip-flop, which is similar to this, except they took care of that situation when you put 1, 1. So what's the JK flip-flop looks like? Again, just like the other one, Q next. The first 3 did not change. We kept them the same. So identical to the SR flip-flop. Jimbo. Should have
It's nice.
should have bought that stock.
Carl did.
You did?
I told him,
Yeah.
he bought 30,000 shares.
Oh my God.
And he bought them at 212 or 236.
Leave it to him, huh?
Yeah, I can't do it. I'm locked out.
Now, just like that SR flip-flop, when it's 0, 0, it's the same as the previous. No change. When it's 0, 1, this will be a 0. 1, 0, this will be what? 1, but here's the difference. When you put 1, 1, it's the previous state complemented. It's the complement of the previous. So if the previous was 0, this becomes 1. If it was 1, it turns to a 0.
What's JK mean?
I don't know.
Just kidding.
Yep, could be just kidding. John and Kathy came up with this.
There you go.
I don't know. I can look actually. I'll Google it and see why they call it JK, but I'm sure that's some significant. Somebody's researching that already. Yep. Again, the output of this depends. So if you were to list all the options, you go J, K, Q previous, and Q next. You'll see next time how we're going to use them in state diagram. I'll do this. If you have 0, 0, and Q previous is 0, notice when both of these have 0, everything stays the same. The next state stays the same. When you have 0, 1, doesn't matter what the previous one is, it goes to what? 0, because that's the reset. JK, just like SR, when you have the 1, 0, that's the set. And now here's the difference. When you put a 1, 1, that's the complement. If the previous state was 0, you'll get what? 1. But if it was a 1, you'll get what? 0. And that's how that flip-flop works. And the last one, I just noticed the clock here. It's a T flip-flop. T stands for toggle. What's a toggle means? So here we go. T and Q next. This is a one input flip-flop. This has two inputs. JK, this has only one input. When T is 0, you leave everything the same. Q next is the same as the previous. When it's 1, guess what's going to happen? You're going to complement the previous state.
Nice.
Some of these are clock, most of them have a clock in them, some don't have a clock in them. The clock, it could be U, but it has like a switch. It works only on the rising, the falling. So here's T, just an example, and this is the previous state, this is the next state. So if you have a 0 and the previous state was 0, when T is 0, leave everything alone. You get a 1, wouldn't change it. But when T is 1, we complement. So if you had a 0 before, it becomes what? 1. If you had a 1 before, it turns to what? 0. And that's the T flip-flop. In next class, we're going to show you how do we use this to actually control this circuit. You need a flip-flop. You can't do this with ROM. You can't do this with PL and PLA. Because it depends, your output depends on the current state, where you are, and your input. All the other ones we did before, your output depends on the input only. Now it depends on two things, your input and the current state. So you have to use a flip-flop for that. We'll wait till after Thanksgiving.